Sir?
Yes, give me a moment. I just have to do something.
Okay.
Yeah.
Uh, you know, can we have a session for PYQs also?
There's already a session in the morning tomorrow, and then again one more on Saturday, right? I don't know if we can fit in more, but I'll
Yeah.
ask and we'll see if it's possible.
Okay, sir.
So yeah, the streaming is started. I'll now share the screen.
Or maybe towards the end of the session, if there are some specific doubts on PYQs, you can take them up if there
Yeah,
is any.
so I'll be mostly taking up theoretical concepts. So as in, I will try to solve problems as well. But if there is time at the end, then we can take up any problem that you wish to discuss. All right. So week 5 and 6 was covered yesterday. So we'll be taking up week 7 and 8 now. So first concept in week 7. Of course, I'll not go into the details of most of the things, but just the like the formula, the main definitions, and so on. Yeah. First definition in the concepts of week 7 is that of equivalent matrices. So if you have two m cross n matrices, many things I'll be writing just shorthand because the detailed notes we have covered later. Covered earlier. If I have two matrices m cross n, these need not be square matrices. Uh, is there a doubt?
No, sir, you may continue.
Yeah. Okay. Okay. Someone's mic was on. Anyway, so the concept of equivalent matrices is for any order matrices. It could be square matrices or non-square matrices because later on what we will discuss similar matrices that is only for
Is it from
square
my side or
matrices.
sir is not speaking anything?
No, we can hear, sir.
No,
I
sir.
think we can hear him.
It's from your side.
So two matrices of the same order m cross n are said to be equivalent if one can be written. We'll just write it as B is equal to QAP. It could be A is equal to QBP as well, but then the orders will change for invertible matrices. Q and P. Now, what should be the order of the matrix Q and order of the matrix P?
Q should be m by m and P should be n by n.
Q is an m cross m matrix, and P is an n cross m. Now, one can be written as another in this form. This is the definition, but most often than not, checking it using this definition is not easy because how will you guarantee whether there exist invertible matrices Q and P which satisfy this or not is not easy to do as it is. So the practical way of checking it is the following equivalent notions.
Rank.
So the first one is you know how to compute rank. So how does one compute rank of a matrix?
Row echelon form.
The
Yeah,
number of non-zero rows.
after you do the
Row
reduction.
echelon form.
Reduction.
Yeah. So after you do the reduction, you can compute the rank of each matrix. And then if the rank agrees, then they are equivalent. And if they're equivalent, this is an if and only if statement. So two matrices are equivalent if and only if their ranks are the same. So this is one way to check.
Sir,
Another
what
way to
is
check
eigenvalues?
what is what?
Eigenvalues.
Eigenvalues in this course, it is not introduced, so I'll not be taking it up now, and it is not necessary for.
You'll get it in machine learning foundations. They will, of course. It's not needed for now.
Oh, okay. Thank you.
Another equivalent formulation of equivalence of matrices is A can be transformed to B using row and column operations. So let's take up an example to make this clear. So suppose I have a matrix, say 1, 3, 2, 4, and
These
let's
are
say
the
this is
only
A.
two. These are the only two things which we can check if you want to check A and B are equivalent.
Well, rank is the easiest thing. No, it is, you know how to, like, there might be other formulations, but for among the things that you know, I think rank and the row operations are easy enough and sufficient also.
And what about trace, sir?
This is for
Trace,
similar matrix.
Okay.
for equivalent matrices, trace might not be equal
Okay.
because you can just take 1, 1, 0, 0. This is a full rank matrix, meaning rank is 2. And this is also a full rank matrix, right? But it
Yes.
So if we could just check the rank of A and B, then we could easily find whether the matrices are similar or not.
yes, that is the way to go. If you want to check for equivalence of matrices, you have to just compute their rank.
So any two matrices of same order, if they have the same rank, they are equivalent.
Yes.
Okay.
Sorry, a quick question here. Both the
Yes.
conditions are not necessary. Either one of them are necessary.
Yeah, this is a separate equivalent formulation. This is a separate equivalent formulation. If rank
Okay.
is equal, that is enough.
Okay. Yeah. I misunderstood. I thought both would be necessary. Sorry.
No. So this, let me call this 1, 2,
Sir,
3. Is there any other doubt?
sir, no, sir. Equivalent matrices implies rank will be equal. Can we say if rank is equal, then definitely they are equivalent?
Yes.
Okay, sir. Thank you.
These are characterizing conditions. So, okay. Now, let us say we have these two matrices. Matrix A is just 1, 2, 3, 4, or 1, 3, 2, 4, and B is 3, 6, 5, X, where X is not known. If I know that given A and B are similar, what is the condition on X?
Similar or equivalent?
Sorry. Yeah, you're right. What is the condition?
Rank of A equals to rank of B.
Yes.
That is the definition, but that is not a condition on X, right? I want a condition on the
Determinant should
value
be
of.
non-zero.
So let us start with the earlier statement that
Value of x should not
sir?
be 10.
X not equal to 10.
Determinant equal.
Determinant is not equal for the equivalent case.
If rank of A,
That should be non-zero, no? If you see the rank of A is 2, and for B, if the rank is need to be true, so determinant need to be not equal to 0.
yes.
Oh, where is sir? Sir got disconnected or what?
He
Yeah.
got disconnected, I guess.
Sir, are you writing something?
Then who is presenting the screen?
Let's just wait.
Yeah, just wait. He should be back.
X can't be minus 11 by 5, I think.
Sir, are you there?
Sir is not there.
Sir got disconnected.
Hello? Yeah. Am I audible?
Yes.
Yes,
Yes,
sir.
Yeah. Yeah.
Yes,
At what point did I get disconnected?
You were starting.
You were starting with
Condition on the x.
calculating the rank.
Equivalent.
Yes, sir. A, B are equivalent. What is the condition on X?
Yeah. So what is the rank of A?
The rank of A is 2.
Yeah. Why is it 2?
The determinant value is not equal to 0.
Yeah. In this case, since it's a square matrix, we can have the rank to be 2. Right?
Sorry,
And
did we? Hello.
yeah.
Did you just say since it's a square matrix, we can have the rank to be 2?
Well, since you have a square matrix, determinant being non-zero means the
Yeah.
rank is full. So yeah, that's
Okay.
that's what I meant to say.
No, the gap between that sentence, I thought you disconnected again. My bad.
Yeah. So here the rank is 2. You can either check that these two column vectors are linearly independent. That way, your this thing is full rank. In any case, or you can perform your row echelon transformations, and then you will get that rank is 2. That much I think you'll be comfortable proving
Yeah.
in any way that you want. Now, what does it mean to say
Sir?
rank of B is equal to 2?
X cannot be equal to 10.
It can't be 10. X value can't be 10.
Yes.
Yes.
Right? X is not equal to 10, and this is the thing. So you can attack questions of this sort where you're given two matrices and then
Can you
you're
please
asked.
explain why is X is not equals to 10?
Okay.
Determinant
once
should not
again,
be 0.
rank of B is 2. Since this is a square matrix, the rank being the total number of columns implies that the determinant is non-zero. So rank of B equal to 2 implies determinant of B is non-zero, which says that 3x minus, 30 is not equal to 0, which is the same as saying x is not equal to 10. Is that okay?
Okay, sir.
Yeah.
Sir, if the order of two matrices are like different, still their rank should be equal in order for them to be equivalent.
You cannot
No.
say, you cannot compare two matrices of different orders.
If there are rectangular matrices,
They should be order should be same, na? M cross N.
they can be rectangular matrices, but both the matrices should have the same order. Only then we can compare equivalence or not equal.
Okay.
Okay. It does not make sense to talk about 2 cross 3, 3 cross 5. That comparison cannot be made.
Transpose should work. 2 cross 3, 3 cross 2. Would that be?
No, even that does not work.
Okay.
Because equivalent matrices, the concept of equivalence comes from the matrices of the same transformation using different bases, which I'll come to now. So the next thing to know. Yes.
Sir, can I say two matrices of same size with same nullity or equivalent?
Yes, because rank nullity theorem, you have rank plus nullity is equal to number of columns. So if rank is the same as saying nullity is the same. But typically checking the dimension of nullity is more difficult than checking the rank. So yeah, more difficult. No, it's the same thing. When you do the row reduction and then get whatever number of pivots you have, the remaining is the nullity. So it's kind of the same thing. And yeah, you can say that nullity being the same is also the same, is also an equivalent formulation. That all right?
Sir, for this question,
yes,
condition of x is not equal to 10.
Yes.
So for
As long
equivalent,
as
we have to calculate the determinant of B.
not necessarily. You have to make sure that the rank is the same. In this case, since you have a
Yes, sir.
square matrix and rank being the total number of columns has an equivalent formulation in terms of determinant, which is determinant not equal to 0. If determinant is not equal to 0 for a square matrix, then the rank of the matrix is equal to the number of columns of the matrix.
Okay, got it, sir.
Okay, there's a few steps over there. Otherwise, you could look at even these two columns, 3, 5, and 6x. Since you want the rank to be 2, you want to have two linearly independent columns. So when do you say 3, 5, and 6x are linearly independent? When they are not multiples of each other. So when will they be multiples of each other? If you have, so 3 into 2 is 6. So 5 into 2 will be 10. So if you have 3, 5 as one column and 6, 10 as the other column, then one column is the double of the other, and then they will be linearly dependent on each other.
Yes, sir.
Right? So that is another way to look at it. If you don't want to look at it from a determinant way, or the brute force method would be to do row echelon transformation of both of these matrices, and then you see that number of pivots has to match, and even that will lead you to the right answer. It does not matter which method you employ.
Yes, sir.
In the case of square matrix.
Sir, I want to share something, sir.
Yes.
Yesterday also, sir, ma'am went explaining in this detail. Everyone was asking the question, and the thing happened was ma'am messed up with this week 6, and it is still uncovered. So better we can do this revision quickly so that we can cover entire week 8 also.
Okay. All right. Then maybe I'll cover the concepts, the definitions, the results, and all that first, and then maybe we'll take up problems at the end. Is that
yes?
Okay?
Yes.
Okay. So are there topics from week 6 that are pending?
Yes, sir. Week 6 is not yet completed. Yeah. Ma'am has left a lot of topics.
That is why we have this TA session
tomorrow. Is a TA session.
Right. Okay. Then it will be covered. So that's okay. Fine. So equivalent matrices, what is the definition and what are the equivalent formulations? Like 1 is equivalent to 2 is equivalent to 3. This is what I wanted to say. 1. So this symbol is if and only if or equivalent. All right. So each one individually is sufficient. But for problems, most of the time you'll be using the rank formulation. And the other thing about equivalent matrices is the following. So suppose I have a transformation. Suppose E from V to W is a transformation, linear transformation. I'll just write LP from on, linear transformation, and you know how to write the matrix of the transformation in given basis. So suppose I have, let's say, beta 1, beta 2 are basis for V, and gamma 1, gamma 2 are basis for W. Then this notation is matrix of T with respect to the basis beta 1, gamma 1. So I'm not going to write that out, but just read this as matrix of the transformation in the with respect to the basis beta 1 and gamma 1 on V and W respectively, and matrix of T. Given any two bases, I can formulate a matrix, right, using by expressing the by using the coefficients as columns. I can write these matrices. Matrix of T with respect to beta 1 gamma 1 and matrix of T with respect to beta 2 gamma 2, and these are equivalent to each other. So after the first round of looking at linear transformations and the concepts in vector spaces, whenever you look at some concept for matrices, you have to ask the corresponding question for linear transformation. So when I say there is a notion of equivalence of matrices, then the natural question would be, what does it mean in the language of vector spaces or transformations of vector spaces? And this is the result in that direction. So if I have a transformation and I have its representation, its matrix representation in different bases, then those matrices are equivalent to each other. That is the result. When I say that these two matrices are equivalent to each other, then I need to either say their rank is the same, or I need to produce some Q and some P such that this is satisfied, and these should be invertible Q and P. So how to obtain this? P is obtained by expressing beta 2 in terms of beta 1. What does it mean to say expressing beta 2 in terms of beta 1? Beta 2 is a set of vectors. Each vector can be, so since these both are bases, each vector in beta 2 can be written as a linear combination of things in beta 1. And those coefficients, if I put in a column, I'll get a matrix, which I call P. And Q is the matrix which is obtained by expressing gamma 1 in terms of gamma 2. So this is a little bit of a tricky thing, because here it is beta 2 in terms of beta 1, but for Q it is gamma 1 in terms of gamma 2. So it is not the same for both things. So that is something that you have to note. And to actually understand this properly, we need to do an example, but I'll postpone that for the end of the session.
Sir,
yeah.
You mean for expressing P, like for P, beta 2 is the domain and beta 1 is the codomain?
No. Beta 2 and beta 1, these are bases, right? These are sets of vectors. So suppose your beta 2 is something like V1, V2, Vn, and beta 1 is V1, let me call this guy V1 prime, V2 prime up to Vn prime, and this is beta 1 is this V1, V2, Vn. These are sets of vectors. So if I write V1 prime.
Could you take one example so that we can understand? Like one example is not too long.
Okay, then we'll postpone this discussion for that example itself later on. Then.
Okay,
So,
So a quick question before you move ahead. Regarding a
yes,
general point, the pair, can you just scroll up slightly?
yes.
The selection of the bases that you did, this beta 2, gamma 2, beta 1, gamma 1, was that arbitrary or
Yes.
that?
This is for
Okay.
an arbitrary thing. You
It
can
might
use
as well have
any.
been beta 1, beta 2, and then gamma 1, gamma 2.
Yes, 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 yes.
Okay.
So if I write beta 1 gamma 1 over here instead of beta 2 gamma 2, then I am bound to get Q inverse and P inverse, right?
No, I'm saying, can you do it? So, for example, matrix of T with respect to beta 1 and beta 2. Could you have placed both
No,
betas
beta
together
1
into
and no, because beta 1 and beta 2 are basis of
basis of the same
V, right?
vector space? Yeah.
Yeah. So what do you mean by matrix of a transformation with respect to one basis? So you need a basis on the domain and a basis on the codomain.
Got it. Okay. Okay, sir.
Yeah. So you can't do a beta 1, beta 2 thing unless it is, of course, a linear operator, which is a transformation from a vector space to itself.
Right. Got it. Thanks.
So
I have a question. Can I ask?
yeah.
Sir, if only there is for codomain, if the only basis is there, like gamma 1 comma 0 and
Okay.
0 comma 1, and other basis is not there, then how we can
Okay.
calculate gamma?
There will always be any number of bases you want. Number of bases
Yeah.
you can
So
take. Are you saying that gamma 1 is the same as gamma 2
no, sir.
is
There is
equal
in the
to?
question they only provided that gamma is equals to 1 comma 0 and 0 comma 1.
Okay. If the basis for some vector space, so most of the time the vector space that you will be dealing with will be Rn, and if the basis is not provided to you in the question, then it is understood that it is the standard basis.
But in the answer, sir, they are providing Q can be the matrix of 0, 1 and 1, 0.
In which
That is
question?
standard basis, right?
Yeah. 0, 1 and 1, 0.
0, 1, 1, 0 is the standard basis. Okay, 1, 0, 0, 1 in that
Yeah,
order,
1,
because
0,
order is
1,
also.
0, 1. So their order is not important, no, sir, in that case.
Order is important, yes. Order is important. Otherwise, you will get some switch in
But sir,
the
if you take
columns.
0, 1 and 1, 0, the order.
You will just get the columns to be swapped of your P and Q.
Okay, sir. Okay.
Right.
Sir, one doubt, sir. Actually,
Yes.
can you just scroll down a little bit?
Okay.
So
This
here
one?
you write. Yeah. Listen. So for equivalence, we know now B is equal to QAP, right?
Yes.
Can we write like A is equal to QBP or something?
Yes. So if you have B is equal to QAP,
Yeah.
and you know these are invertible matrices, right?
Yeah, of course.
So I'll do Q inverse B is equal to Q inverse Q AB. But Q inverse Q is identity. So I can just remove that guy. And then it'll be multiplied by A inverse on this side. What I'll get is not A inverse, sorry, P inverse on this side. Then you'll have APP inverse, which is A. So you have written A is equal to something B something. It is not QBP, but it is Q inverse BP inverse. So this is called symmetry of the equivalent of a relation. So this equivalence of matrices is symmetric in the sense that if A is equivalent to B, then B is equivalent to A.
Yes, sir.
And that is also clear because rank is equal, right? Rank of A is equal to rank of B is a symmetric relation. So, and the formal way to see it is this.
Okay.
Sir, I could understand the expression of P expressing P's beta 2 in terms of beta 1. Like, I couldn't understand the expression.
We'll get to that when we get when we take up an example later.
Sir,
Let's
what
finish
does it
the.
mean by Q is always unique?
What is meant by Q is always unique.
Yeah.
So can you write A is equal to QBP or B is equal to QAP? So B is equal to QAP if you write it. And can you write B as Q prime AP prime?
No, sir, no.
So this is
Q is still same.
This, I don't know if it is unique or not. I believe it is unique. Is it mentioned somewhere that it is unique?
No, sir, it is not unique. The option is whatever the matrix P we choose, Q is always unique. That is the first statement.
Where are you? Are you referring to some question or?
Yeah, I just write down my doubts and I am asking you.
Okay. This uniqueness, I am not sure. Let me think about it a little bit more.
Okay, sir. Okay. In
Yeah,
the end of the
you
session,
can.
I will tell you the question.
Okay.
Okay, sir.
You cannot read a question and expect me to understand. So please spell it out when you're
Yeah,
asking
yes.
the question. Yeah. Okay. Next, let's go to similarity of matrices. Now, equivalence of matrices is for any order matrices, but similarity of matrices is a concept that is only there for square matrices. Okay. And in this case, A and B, if you have A and B, which are M cross M matrices, then are said to be similar if B is equal to P inverse AP. So instead of QAP, where my Q and P could possibly be different, here we want Q actually to be the inverse of P. So this imposes more restrictions. And in this case, we are only having square matrices, A and B. The consequences of this, and so this is an important thing to note, that in the case of equivalence of matrices, these all were equivalent conditions. So you can check rank of A is equal to rank of B and then you're done. Or if you can transform A to B using row and column operations, you're done. But in this case, that is not true. So similar implies rank of A is equal to rank of B. Similar implies equivalent. So these square matrices you can see as just any matrices and ask whether they're equivalent with each other, but they're equivalent with each other for the obvious reason that if you take Q is equal to P inverse, then you have that form B is equal to Q. So similar implies equivalent. Similar implies determinant of A is equal to determinant of B. Similar also implies trace of A is equal to trace of B. But none of these are two-way. As in, if you have rank of A is equal to rank of B, then it does not say that it is similar. So to say something is not similar is not easy. I mean, you can check these things, but that will not be sufficient. So, but in the problems that you will take up, most of the time, these things will be sufficient. You can check the rank, you can check the determinant, you can check the trace, and then if you don't, but of course, that does not conclusively tell you that it is similar. Mostly the questions might be in the negative. So you
So
find the
trace is
condition.
Sir, can you please
the
explain
sum
what
of
is?
diagonal elements, right?
Yes.
Okay.
So equivalent matrices are like a superset of similar matrices in that sense.
No. Yeah. Right. Similar. This is equivalent. Similar matrices are a smaller set, so you require more conditions, more stronger
Stringent.
conditions.
Got it. Yeah.
Trace is sum of our diagonal elements. And trace, of course, makes sense because we are in square matrix setup.
Sir, for matrix to be similar, so these all four conditions need to be satisfied, right?
Yes, these are necessary conditions. Yes.
So if any one condition fail, then it's not similar.
Yes.
Okay.
So as far as the quiz is concerned, as long as we check that all these conditions are matching, we should be good to go for similarity.
this will be sufficient. Yes, as in you can take for example this question itself. What can you say about X if these two matrices are similar? Can these matrices be similar?
Trace has to be same.
X.
So actually similarity implies x not equal to 10, but simply by x not equal to 10 we cannot say it is similar. No, sir.
Yes, we cannot say that. But what are the conditions that we have seen so far? We need at least this, right? Determinant
X has
of
to
A
be
is
2
equal to
actually.
determinant
Equal to that of B,
B.
huh?
So what
It
does
can't
this
be
say?
similar, sir, because the determinant can't be same.
X equal
Determinant,
to 8 by 3.
Yeah,
you have
if we take
3x minus 30 is equal to, what is this, minus 2? So
X
this will give you
20.
some value of x. And if you say trace of A is equal to trace of B,
Yeah, that will give another value.
this will give me x is equal to 2.
X equal
So
2, yes.
that cannot be satisfied simultaneously. So these can never be
Yeah.
similar to each other, right? And what
Sir,
are all the matrices similar to the identity matrix?
yes, sir.
What are, this is
scalar
a question.
matrices.
What?
Sir, so being similar required all those four properties, right? All those four.
Yes, yes.
So only identity matrices is similar to itself, or do we even have other matrices?
Let's say IN, general IN.
Yeah.
Sir, excuse
So
me,
what
sir.
is the
I have
answer?
one doubt in that
Alpha I,
expression, sir.
What matrices are similar to
scalar
identity?
Identity
matrices.
matrix.
Sir, excuse me,
Okay,
sir.
let's just a moment. Let's take this
Yes, sir.
question.
Am I
So
audible?
yeah, you're audible. You said scalar matrices, right?
Oh, yes.
But it
By
is not also
definition,
true, no? If we take scalar matrix.
if it is scalar matrix, what happens?
Trace will not. Maybe trace will
It's
not.
not always true.
So all scalar matrices do not work, right?
Yes.
Trace
So
value
you
will be
look at you take the definition itself. If there is a B which is similar to IN, I should be able to write B as P inverse IP. But this is nothing but P inverse P, which is nothing but I. So B is
I.
actually equal to I.
Sir,
Right?
actually,
Yes.
what does a P mean for, sir?
Sorry.
What does it actually P matrices mean for?
Yes, sir. That's a doubt.
I understand that the concept of B equal to P inverse of AP. But what does a
Yes.
P matrices actually represent? I couldn't get that.
So do you want an explanation in terms of something similar to this?
Yes, sir. Yes, sir. That's the thing.
So that is the next thing. So here, this is one comment that the only matrix similar to identity is itself. So irrespective of what matrix you have, a matrix is always similar to itself. That is also clear, right? Because
Yes.
if you take P is
Yes.
equal to identity, you can write A is equal to identity inverse AI. So
It is an equivalent relation.
it's an equivalence relation, yes.
The P could be
So
in any matrix, or that should be defined something
it
should be there.
as long as it is invertible, it is fine. If I can find a P such that this equation is satisfied, then I have similarity of matrices. So what is it in terms of linear transformations? So in
Sorry,
this
sir,
case,
just before we move on to the new concept, just a quick question. The four conditions that you gave, right, for
yes,
similarity, given the first
yes,
condition, isn't the second one redundant?
yes, it is. I just wrote
Okay,
it
so
separately. That's all.
got it. So
This
basically,
is
we have three
actually
checks for
this
similarity.
is yes.
Okay.
This is the same as this because rank being equal is the same as equivalent matrix.
Right. Thanks.
Sir, if along with the above conditions, if eigenvectors are also same, then can we conclude they are similar?
along with all of this, I'm not going to take up that question because eigenvalues are not part of the course and we have to complete the thing. So if I have a linear operator, meaning a transformation from V to V, then now instead of beta 1, beta 2, gamma 1, gamma 2, I look at beta and beta and gamma. Over here also I look at beta and gamma. I can look at matrix of the transformation with respect to beta beta and matrix of the transformation with respect to gamma gamma. Right. So you want to look at a basis on the domain, a basis on the codomain. So in this case, since the domain and the codomain are the same, you can express your matrices with the same basis for the domain and the codomain, and what you get are similar matrices. Now, if I want to express let's say gamma in terms of beta, then this P can be obtained by expressing gamma in terms of beta. All right. So this is the interpretation of similar matrices when it comes to linear operators or linear transformations from a space to its set. So that is why you have this square matrix, this notion only applicable for square matrices. And the way to get the P in this case is by expressing one basis in terms of the other. And that's it about equivalence and similarity. So next we'll take up affine subspaces.
Sir,
Yes.
can you explain that notation of M of T?
So any matrix can be to write the matrix of a transformation. You need a basis on the domain and the codomain, right? So M of T over here, when I wrote M of T beta 1 gamma 1 or M of T beta 2 gamma 2, it means matrix of the representation T, matrix representation of the transformation T with beta 2 on the domain and gamma 2 on the codomain. But in this case, since domain and codomain are the same, you can take the same basis for both of them. And that is why you can have gamma gamma and beta beta. Right. On the domain and codomain, I have the same basis. I express the target vectors or the image vectors in terms of the same basis. And that is the matrix of M of T. Gamma gamma means matrix representation of the transformation T with gamma as the basis on both domain and codomain. And M of T beta beta means matrix representation of the transformation T with beta on the domain as well as the code. So next on to affine subspaces. Affine subspaces, affine transformations, all of these things are small concept in which just lets you do certain things on things more than linear subspaces. They behave like linear subspaces only up to a translation. So what does that mean? If I can write a set as a vector,
if you add one vector in that linear trans.
Yeah. Yes, if you take a linear subspace and add a vector, then what I get, add a vector to each of the vectors, right? It's not that I'm adding it to one vector. So what I get is called an affine subspace. So to see a picture again, a linear subspace, or say a one-dimensional linear subspace of R2 would look like a line through the origin. Now, if I add a vector, let us say I add a vector in this direction, a vector which is like -1, 1 or something, what I get is a subset of the form this. Right.
So
So this is
is it
still a
one
straight
dimensional
line.
or two-dimensional? I think it is a two-dimensional. Y equal to x. It's passing through
Y
the
is equal
origin.
to x is one dimensional, right? It's a line through the origin. It's one dimension.
Okay, sir. Okay.
Yeah. So by using different vectors v, we can actually get all the lines in this, all the lines in R2. So while linear subspaces have the restriction that they have to pass through the origin, these affine subspaces don't have that restriction. They still retain the linear structure. So if you look at affine subspaces of R3, R2, for example,
X plus by equals to d.
R2. Now, what are linear subspaces of R2? Can someone quickly recall?
It will add it to
Lines.
0.
Lines passing through origin.
Are they
Origin
the
plus
only ones?
Ax plus by equal to 0, I think.
Yes, that is one class, but is that all of them? Linear subspaces?
No, sir. It's not all of them.
So
F
linear
Can
comma
you explain
subspaces
this?
Are
linear.
point, line, and itself.
Yes, point meaning actually zero. So linear subspaces are the zero subspace, lines to the origin, as well as the entire plane. So
Yeah.
affine subspaces are translates of that, or a point
Point
plus that.
linear and the vectors
So
which is
here you
rely on
have
that.
points, lines, and the entire plane.
Yeah.
So here,
When you say entire plane, it's the same thing, right? It's a subspace of itself, is what you mean.
yes, it's a subspace, like the whole subspace. If you move by some vector, also it remains the whole subspace.
Okay. Yeah.
So, but here this has changed from here. You didn't have all the points as vector subspaces. You had only one specific point, the zero vector, only as your zero-dimensional subspace. But affine subspaces could be any point and any line. We have removed the restriction of line through the origin. So we are capturing a bigger class of examples using affine subspaces. So more
Okay.
generally, if you look at affine subspaces of Rn, you will have points, lines, planes. So the linear subspaces of Rn you look at as origin, lines through the origin, planes through the origin, and higher dimensional planes through the origin, or higher dimensional subspaces through the origin. So this through the origin is something that gets removed when you're talking about affine subspaces, because you can just translate it by a point. So instead of planes through the origin, you'll have planes not necessarily passing through the origin, any plane. So any two-dimensional subspace, and so on. Planes, I just write etc. They still have a linear structure, but they don't pass through the origin as well. Okay, and another classical and probably the most important class of examples. Is there a doubt?
Yeah, maybe we'll finish this and then I'll ask. It was about that R2 thing.
Okay.
I'll wait.
Okay. So the prototypical examples of linear subspaces are solution systems of equations of the form this, right? Ax equal to 0. Let me write it as x in Rn such that Ax tilde is equal to 0 is a linear subspace of Rn.
Yeah, it is a U.
But what happens if I write, instead of a homogeneous system, I look at Ax tilde is B for some maybe non-zero B.
We got affine subspace.
This is an affine subspace, but there is something that we are missing.
The
Can
U
someone point out?
vector something.
provided that the system has a solution. Because if the system doesn't have a solution, then this set is empty set, right?
Yes.
So when does such a system have a solution? One way to say it is B tilde is in the column span of A, right?
The element of third column all are 0. Third row, sorry, sir.
What is third row? Because we may have any number of rows and columns, right? So
Yeah,
third row is
the
not the
last,
way to say.
I think.
So the proper way to say it is B tilde is in the column space of A. What is the column space of A? The vectors which you get by taking A times X, and you vary X in all of Rn, then you'll get a subspace. This Ax tilde, where you vary X tilde, this thing is the column space, correct? And if this subspace contains B, then you have a solution. So whether B is in the column space of A or not is something that you have to check. So to ensure whether or not the system has a solution.
So can we take an example?
Okay, so take for example, say 1, 2, 3, and I'm taking a simple sort of example. Times xy is equal to 0 and 3, something like that. So this is a system of, this is your x, this is your x tilde, and this is your b tilde, right? What is the system of equations that you have? X plus 2y I.
There's a chat also, sir.
Yeah. So x plus 2y plus 3z is equal to 0. And I want 2x plus 4y plus 6z is equal to 3. But can this happen?
No.
This is basically same.
Number of variables is more than number of
This is
There's a contradiction.
the same. This is the same as x plus 2y plus 3z is equal to 3 by 2. Right? I want x plus 2y plus 3z equal to 0 as well as 3 by 2. So you'll get 0 is equal to 3 by 2, which is not possible for any value. So there is no x, y, z in R3 such that this system of equations has a solution. So if you write down for this A, if you write down x, y, z such that A times x, y, z is equal to 0, 3, this set is the empty set. Correct?
Yes. Yes,
So
sir.
empty set is not an affine subspace. Affine subspace is the translate of a linear subspace, and that has to have at least one point. But as long as it has one point, it turns out to be an affine subspace. This is, I'm not going to go into the proof of that, but you can just make note of this. This is the important statement that solutions to systems of equations, not necessarily homogeneous, form affine subspaces, provided that a solution exists in the first place. And there are examples where solution does not exist. And what you need to verify is whether or not that system has a solution. And let us say A is invertible. Say if A is an invertible square matrix, then this will have a solution, right? I can just multiply by A inverse. And there are some other conditions, like if you have specific numbers, then you can of course verify whether the system has a solution or not by solving the system of equations using whichever method that you know. But in general, the thing that is required is that B is in the column space of A, which means that there exists an X such that AX is equal to B, these are all reformulating the same statement. So, okay, yeah, there are many raised hands.
Yeah. So, can I ask the question, sir?
Yes, Go ahead.
Yeah. So when you were talking about the translation of R2, if you can go scroll slightly up, I was
Okay.
just trying to I was trying to get a visualization for that. So let's say if you're talking about the XY plane, would translation be something like moving it up down along the Z axis or angularly rotating it or something like that?
You could think of it that way, but if this is your only doubt, I think we'll take it up at the end of the session, because
Sure.
this will not be very relevant to the revision session, the theme of
Got
the
it.
thing.
Yeah.
Okay.
It's fine. So yeah,
Okay.
I'll ask it
Yeah.
again at the end.
Yeah. Any
Sir,
other question? Yeah.
one doubt, sir, actually
Yes,
regarding.
sir.
So it's affine subspace is not a vector space, right? But it does not pass
It's
from
not a
0,
vector space. Yes, it's not a vector subspace. I mean, vector subspaces are also affine subspaces, but not all affine subspaces are vector spaces. Again, affine subspace is a bigger class. It's a superset.
Oh, okay. Thanks.
Yeah. So, for example, if I ask, is x tilde in Rn such that ax tilde equal to 0, is it an affine subspace? The answer is yes, because a vector subspace is an affine subspace. You can just write a vector subspace as u 0 plus u, where u is your linear subspace, vector subspace. So vector subspaces are affine subspaces, but not all affine subspaces are vector spaces.
So similar to that equivalence similarity thing, affine
Yes,
subspaces
yes,
are like a superset.
yes.
Okay.
Yes, sir.
Yeah.
Can I say R2 is an affine subspace of R3?
Yes. R2 is a vector subspace, right? And a vector subspace is an affine subspace. So R2 is an affine subspace.
So can we say all the homogeneous systems are in affine subspace?
Not homogeneous systems. Solution to a given homogeneous system of equations, yes, because once again, that's a vector subspace, as you know.
Yes.
Yeah. So a solution to a given system of a homogeneous system of equations is a vector subspace and hence an affine subspace.
Okay.
Yeah. So next we'll be looking at affine transformations. This is somewhat.
Sir, just a small request. I think the concept of affine subspace is more or less clear, but if you could take up some example problems towards the end of
Yeah,
what we could
I'll be.
expect in the course.
Yeah. So I'll be taking only examples at the end, and there are specific problem solving sessions, right? So problem solving will be done then, I think, because here I need to revise the concept. So
Yes, sir. Sure.
that's the primary purpose. So here, if a map, so suppose L and L prime are affine subspaces, then F. So this L can be written as V plus U, and this can be written as F of V plus U prime. So since these are affine subspaces, there is a vector and a subspace such that L is equal to this and L prime is equal to F of V plus U prime. So there are two subspaces, linear subspaces, which L and L prime are translates of. And if I write it like this is an affine transformation if this map G from U to U prime, the underlying subspaces, there must be a map which I define as this. And if this is linear, is a linear transformation. So this is somewhat of an unnatural looking definition. But what is actually happening is just you're coming back to you're removing the part from U plus V, which is that extra part, which is the translation that you're removing, and you're looking at the remaining transformation. And that has to be a linear transformation. So this definition as it is not that important. What is important is all affine transformations, suppose, come from linear transformations itself. So if P from, let's say, U to U prime is a linear transformation, because the sort of questions that may be asked are, is this an affine transformation or not? So I'm going to tell you how to check that. So if this is a linear transformation, then f from, let's say, v plus u to v prime plus u prime or let me just call it v plus u to, v prime plus t of u, because t of u is once again a subspace, correct? So this defined by f of v plus u. Any element in v plus capital U will look like v plus small u. This is v prime plus t of u. What is this? What is actually happening over here is, the way you have to look at affine transformations is that they are some vector plus a linear transformation.
Yeah, we need basis.
We don't need basis just to understand this. What I'm saying is that any affine transformation can be written as a sum vector plus a linear transformation. Just like an affine subspace is a vector plus a linear subspace, an affine transformation is a vector plus a linear transformation. So suppose I'm given a map f of x, y, z is x plus 3y plus 2. And this is, say, from R2 to R3 to R2. X plus 4z plus 9, something like that. So is this an affine transformation? So what you have to check is, can I write every element in this form?
Yes, sir.
Why can I write that?
Sir, 2,9, I think.
Yeah. So if I have this thing 2,9
x
plus x plus 3y
x plus 4z.
X plus 4z. So this is this vector plus, let me call this t of
Transformation.
x, y, z. So typically what you can do is input 0, 0, 0 over here. If it is from R3 itself, if it is from given, if it is some translate which does not pass through this, then you'll have to make corresponding adjustments. And if you can write it in this way, a vector plus a linear transformation, then this is an affine transformation. As opposed to, let's say, if I have f prime or f2 of xy, which is, say, x square plus 2 and y cube plus 3. This will not be, because
it is not a linear transformation. X is cube.
Yes, x square plus x square y cube.
Yeah.
This is not a linear transformation.
Linear.
So this is not an affine transformation because the corresponding guy is not a linear transformation.
Yeah.
Right. So this is it about affine subspaces and transformations.
So can you show the condition one more time? Can you just scroll up?
Yes.
Okay, thanks.
Right. Next we come to dot products, etc. I'll tell you what all of those things are. So in Rn, you know what dot products are. If I have x1, x2, xn, you know what it means to say xn dot x tilde dot y tilde. This is nothing but summation xi y.
Linear combination, right?
It's not a linear combination, no, but it is just coordinate-wise multiplication and then adding them.
So isn't that the same as linear combination?
What is linear combination of what?
Of those two, I mean, x1 dot dot xn and y1 dot dot yn.
So this is a vector, and this is a scalar. Right? So this is something like Rn cross Rn to R. A linear combination is some scalar times some vector, and then you're adding them all together. So your linear combination is typically of the form Ci-Vi, and this whole thing is a vector.
Okay.
You could look at Yi's as one-dimensional vectors and then say they are linear combination, but yeah, that's not an interpretation that helps us in any analysis. But the dot product is something that you're very familiar with. You just take x1, y1, x2, y2 and add them all up. And in Rn, this gives rise to a notion of length, which is defined as x dot x or x tilde dot x tilde. If I take the inner product of some vector with itself, I get the square of its length. And to write it, it is just x1 square, xn square. This is also easy to see, right? This is in coordinate geometry. If you have a point xy, the length of that is x square plus y square, square root of x square plus y square. So, which is the same as xy dot xy under square. And then the length of, the angle between two vectors is also known. It is x dot y divided by norm of x or length of x times length of y. This also can be derived using, at least in R2, using by observing certain things, which must have already been done in the earlier sessions, or it is there in the process lectures. So, and all of this is very well known. To generalize this notion to arbitrary vector spaces, we need something that generalizes this dot product. So, and that is an inner product. So, just like this was a map from Rn cross Rn to R, meaning it takes input as two vectors and gives the output as one vector. Here, output as a scalar. The same thing happens in the case of a general inner product, V cross V to R, and the properties that it needs to satisfy is linearity, meaning, so typically it is denoted by these angled brackets. So if I have A V1 plus B V2 with V3, this has to be A times V1 V3. I'm doing two things together over here. One is scalar multiplication and one is addition. So if I have the sum of two vectors, they will split as AV1 V3 plus inner product of BV2 V3, and then the scalars come out. So linearity meaning scalar multiplication also comes out and addition also splits both of them. And then if I look at the inner product of two vectors, the order in which you take them does not matter. That is called symmetry. And the last one is positive definiteness. Which is the inner product of a vector with itself is always greater than or equal to 0. And this is 0 if and only if V is 0. Right. So all of these things happen for dot product. This is, you should think of, you should have, could you repeat that? I didn't hear you.
Sir, what is this V cross V gives R, sir. Can you please explain inner product?
This V cross V is just the product set.
Yes, sir. But what is R, sir? Real.
R is the real numbers, yes. The field of real numbers, the scalars. So it just says that it takes input as two vectors.
Okay.
And in some sense, it multiplies them or dot product of them. It is the generalization of the dot product. So it's like the dot product, and it gives you a real number as the value.
Got it, sir.
And that sort of product has these three properties, where if I take VW, I multiply V with W or W with V, it does not matter. That is symmetry, the second property. And
Yes,
the
sir.
product of something with itself is always greater than or equal to zero. I'll think of this as square of a number has to be positive, and it is zero only when the number itself is zero. So a similar thing holds for at a vector level now. So, and linearity is also something similar.
Yes, sir.
Whenever there are technical definitions, go back to the prototypical examples. So in this case, you have two prototypical examples. You have the dot product on Rn, or even more simply, just multiplication of numbers. So to verify whether or not something is an inner product, you have to verify these three conditions. And the problems of that sort are more theoretical. For example, let's take x1, y1. This is one of the examples that was brought up in the x1, x2 in one of the earlier instructor sessions. And I had incorrectly said that this is an inner product. So can someone say why this is not an inner product? So I define the product of x1, y1 and x2, y2 as x1, x2 plus y1, y2 minus x1, y2 plus x2, y1. Which of the properties fails here?
So I think the u comma u.
So symmetry will not.
Symmetry does hold, right? So if I exchange x2, so if I change the ones and twos, which is what I need to do for checking symmetry, I still get the same thing, no?
Positivity, sir. The third.
1.
Yes, sir.
Yes,
Is
so,
u comma.
What about 1010? Does that give me a contradiction? This will be 1 plus 0 minus x1, y2, x2, y1. No, this will be fine. Maybe 1001.
Symmetrics are both vectors of this, right?
Wait, let me see. 100. Okay, 1001 can be anything. Come again?
Positivity, we need same vectors.
Yes. So 1111 will be 1 plus 1 minus 1 plus 1. So this will be 0. So I cannot have the inner product of a vector with itself to be 0 unless the vector itself is 0. And this vector is not the 0 vector. So this should not happen. So therefore, this is not an inner product. And to verify linearity and symmetry, in this case, linearity and symmetry do hold. And to verify that, it is just notationally a little bit heavy, but I'm sure you can do that for yourself. But it is obvious that any vector of the form x comma x, if you take the product of that with itself, it will give you 0. So this is not an inner product. The square of a number cannot be 0 unless the number itself is 0. This, we are looking at a vector space. So the product of a vector with itself cannot be 0 unless the vector itself is 0. So that is why this is not an inner product. Now, once I have an inner product, I can get all of these things back. So what did I use to define the notion of a length? I just used the inner product of a vector with itself. To determine the angle between two vectors, again, I used the dot product divided by length, which is also defined using the dot product. So in an inner product space, by which I mean, if I have a vector space with this thing, this is called an inner product space. So in an inner product space, I have notion of length, right? Length of a vector.
भाई mic off कर ले.
Can you please mute your mic?
Mic.
All right, let's continue. So this is called the length of the vector square. So in this double vertical lines, V is the notation for length of the vector V. The square of the length of a vector is given by the inner product of the vector with itself. And angle between vectors, angle theta between V and W, that is cos theta. Once again, instead of dot product, you just have the given inner product divided by the length of the vectors in the given inner product with respect to the given inner product. So this gives you a notion of length, angle, and this is also known as norm. This norm, this thing is called length of V or norm of V. And then there is the general definition of a norm and so on, but that is not as important. What we need is the notion of lengths and angles, because the lengths of, why did we go from all these vector spaces inner, why did we even
Excuse me, sir.
introduce this inner product? Is there a doubt?
Yes, sir. So the norm is the length of V, right?
Yes,
So
length of V or norm of V are
norm
same.
square
They
is
are,
not the length.
no,
I
square
think
is not the length. No,
I think he's talking about L2 now. That two, that is what he's talking about.
no, length and norm are just two different words for the same thing, which is square root of the inner product of V with itself.
So you have written norm square over there.
Yeah, this is norm square.
Okay.
This is norm square is inner product of V with V, and this thing is called length of V or norm of V.
Okay, okay, sir.
So the formula is going to be in under root, right?
Norm of V is equal to square root of inner product VV. That's correct. But here I've written norm of V square is VV. That's also correct, right? It's the same thing. These are positive functions, so there's no plus minus business.
Sir, how do they define the notion of V, comma?
Not able to hear you clearly. Can you?
Sir, you have defined in the product.
I can't hear
V,
you.
comma. Just a second. You have defined in the product expression.
Yes. Inner
Y,
product. The
comma,
example,
Y,
or
comma.
are you talking about this?
No, below. The last. How do we define this notion? V, comma, angle bracket means?
So if you are given an inner product, I'm saying you can define what is the length and an angle. That thing is given to you. This angle bracket is given to you. Given the angle bracket on a vector space, you can define what is length of a vector, which is given by angle bracket of V with itself. This is a function that is part of the given data. What angle bracket means. Okay. All right. So next is orthogonality. V is said to be orthogonal to W if angle between V and W is 90 degrees. But what is that in terms of the inner product? Because we know that if angle between V and W is 90 degrees, then what does this say? Cos of 90 degrees is 0. So the numerator has to be
0.
So with respect to a given inner product, if I have the inner product of two vectors to be equal to 0, then those two vectors are said to be orthogonal to each other. And orthogonality, so suppose V1 to Vn is a set of orthogonal vectors. Well, there's a technical small thing over here, non-zero orthogonal vectors. Then V1 to Vn is a linearly independent set. All right. So orthogonality implies linear independence. So instead of having to check everything, as in make a matrix and do some Gaussian elimination and check if all of those, there are no zeros and stuff, the usual way to check linear independence, there is a shorter way, as in it's not exactly a shorter way because orthogonality holds for much fewer vectors. So, but if you know that some given set is orthogonal, then it is linearly independent. So this is one way to get a basis. You can keep constructing using Gram-Schmidt orthonormalization, which I will say later. You can construct bases. So these bases, which are orthogonal or orthonormal, are more important because they can be used to determine the coefficients of any linear combination very easily. So further,
for projection,
yeah, if norm of Vi is equal to 1, this is not a new point, so let me erase this, for all I, then this V1 to Vn is said to be an orthonormal set or ON set. I'm just using ON over here to save some time, but orthonormal. So what are the two things that you have to check if you want to say something is orthonormal?
the norm
One
should be
is
1.
the norm of all
Each
each of the vectors should be 1, and pairwise Vi, Vj should be orthogonal to each other.
If they are orthonormal set, they're orthogonal.
Yes, orthonormal is a stricter condition.
Yeah.
So if you have the number of vectors in this set to be equal to the dimension of the space that you're working in, then you will get a basis because orthogonality automatically implies linearly independent, and linear independent of dimension many vectors is a basis. So suppose V1 up to Vn is an orthonormal basis. Now, how to get an orthonormal basis, we'll see soon. But suppose you are given an orthonormal basis, then how will I express any vector in the vector space as a linear combination of this? So typically I can write it as C1 V1 plus C2 V2 plus Cn Vn, right? So any vector can be written uniquely as a linear combination of these. But the advantage of working with an orthonormal basis is that these coefficients can be found out just by computing the inner product. I take the given vector, and if I compute the inner product with each of the elements, then I get this. So let us look at an example for this. I think an example is required. So express, let's say 3, 2 or something in the basis 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root. So is this an orthonormal set is the first thing that you have to check. The length of this is what?
Is 1.
1 by root 2 square plus 1 by root 2 square,
Half
which
plus
is half plus half, which is 1, and the square root of that, which is 1. So similarly, this is also a unit vector. And if I take the dot product of this, so when it is asked to
That is
check
also 0.
something, when an inner product is not specified and there is an inner product required for the question, you have to assume that it is a standard inner product.
Yes, sir.
If it is some non-standard thing, then it will be specified in the question. So here I have, using the standard inner product, that these are orthogonal to each other and they are of unit length. So this is a orthonormal basis because I'm in a two-dimensional space R2 and I have two vectors which are orthonormal to each other. This is a basis, this is an orthonormal basis. So I can write 3, 2 as C1 times 1 by root 2, 1 by root 2 plus C2 times 1 by root 2 minus 1 by root 2. Now, how do I compute what C1 and C2 are? In this case, you can maybe just eyeball it, but in general, even if it is not very easy to solve the system of equations that arise out of this, you can just take the inner product of this with this. I take my given vector and take the inner product with the first vector in my basis. What I get is 5 by root 2, correct? And then if I take the same thing with the second basis vector, that will be the second coefficient. And that will just be 1 by root. And this you can check that this is correct. So in order to find coefficients in terms of an orthonormal basis, all you have to do is take the inner product with the basis vector. So if you want to find the coefficient of some basis vector, you just take inner product of the given vector with that basis vector. But all of this is fine. Yes.
One down, sir, actually. Can you just scroll down? As you say, when you define a standard inner product, let's say x1, y1 plus x2, y2.
Yes.
And let's say we didn't define a standard product. We define some arbitrary product.
Mm-hmm.
And we get, after multiplying v1, v2, we get 0, right?
Okay.
And but in standard way, it is not 0. Then it is orthonormal, means it orthogonal or not?
So orthogonal or orthonormal makes sense in the universe that you're working, and the universe that you're working with has to specify what inner product. So with respect to this inner product, it is orthogonal. This is a correct statement to make. Without the knowledge of what inner product that you're using, that statement does not make sense. So there might be two vectors which are orthogonal with respect to standard inner product, but which are not orthogonal to some other inner product, or the other way as well. Something that is not orthogonal with respect to the inner product, but orthogonal with respect to some other inner product.
Oh, that's main.
Yeah, that can happen. But in the question, or in whenever you're doing any analysis, what inner product you're working with will be clear. And with respect to that, you have to construct the orthonormal basis or compute the inner product to get the coefficients. All right. So this is how you express some vector in a given orthonormal basis. Now, next, we look at projection. The idea of projection is just that you have, for at least from a vector to a vector, it is what is the component of a given vector along another vector. It is denoted by projection of a vector v onto w and it is given by the formula VW divided by norm of W square times W. Of course, it is something that has to lie along W, right? It is the component of V along W. So, and the coefficient turns out to be inner product of V with W divided by norm of W square. So this is known as the projection of V onto W. And once you have the knowledge of projection of V onto W, a vector. So this is V and W in our given vector space V with a given inner product. Now, if I have a subspace W, then I can extend this definition and say this is projection of V onto Wi, where I is running from say 1 to k, where W1, Wk is an orthonormal basis of the subspace W. So the first step is understanding what vector projection, like projection of a vector onto another vector is. And given that information, you can extend that definition to understand what the projection of a vector onto a subspace is. So given a subspace, if I am given an orthonormal basis of that subspace, then I can take the projection of my given vector onto each vector, and then I can look at the sum of all those projections, and that happens to be the projection of the vector onto the given subspace. Now, using both of these things, I can define projection operator. Which is a map. So projection operator onto a subspace W. This is a map from V to V. So what is PW of a vector V? So if I want to define a map from a vector space to another vector space, I have to say what is the image of this thing. So I just simply call it projection of the vector V onto the subspace W. So this is a very important operator. And as we have seen over here, the idea is that the projection of a vector onto a subspace or a vector is the shadow of that. It's to be thought of as the shadow of the vector onto the given line or a subspace. Now, using that geometric understanding, the following properties are sort of immediate, that kernel of PW is W per, which is the set of all vectors in V such that inner product of V comma W is 0.
Sir, what do we call that notation, W and that thing?
So this is per. So this is short for perpendicular.
Oh, okay, okay.
Okay. So it is PERP per, which is short for perpendicular, which is denoted by this orthogonality symbol as a superscript for the W. So if you are given a subspace W, then all of the vectors which are orthogonal to that subspace don't cast a shadow, right? It gives you 0 shadow. If it is some slanted thing, it will still cast a shadow, and that is the projection. But if you have something which is shooting out upright, and this is a visualization that makes more sense in up to 3 dimensions, and later on it is just abstraction of the same thing. So if you look at all possible vectors which are orthogonal to every single vector in the given subspace, then that will have 0 projection onto the subspace. This is one thing. And I'll take up an example for this as well. So bear with the notations for a bit. Image of the projection. So the shadow lies on the ground, right? And the ground is your subspace W. So image of this is always W. So hidden in this is that dimension of W perp is equal to anyone. So suppose this is dimension of Okay, you can just write it in terms of dimension of V and dimension of W. Can anyone quickly say what this should be?
Dimension of W.
Is nothing but it is a rank of
V minus W.
So it should be V minus W because, so this is what? This is your nullity, right? Dimension of the kernel is called nullity. And
it is
rank
the rank.
plus nullity. So rank plus nullity should give me the dimension of the domain. So image is W. So your rank is the dimension of W. And nullity is the dimension of the kernel, which happens to be W perpendicular. So the dimension of W per plus dimension of W should be dimension of V. This is your rank nullity theorem. So if I rearrange that, what I get is dimension of W per is V minus dimension of V minus dimension of W. So this is about the kernel and image, and there are certain other interesting properties. So projection of V equal to, for I'm looking at vectors in W. So if I take a vector in W and look at its projection, what would it be? Any guesses?
V.
It has to be V, right? So once again, thinking of these things as shadows. If I look at a vector in the plane itself, the shadow will be the whole thing. So projection of V will just be V. If my starting vector itself is a thing in my given subspace, then this happens. So if there are, so the first thing, if you want to see when you're asked to calculate the projection of a vector onto some subspace, is whether that vector is actually just in the subspace. If that is the case, then the projection is the whole is the given vector itself. And then there are other properties which I'll just state over here. All these will follow from preliminary analysis, but most of the proof of all these things are not that important. But it is good to know all of these things. So we will take up an example once I finish in another 5-10 minutes. I'll finish the thing and I'll take up an example for the projection operator.
Sir?
Which will, yes.
For the third one, there is no shadow, if we understand it practically.
If
V belongs
the
to
shadow of
W
this
itself,
thing,
there is
so
no shadow at all.
no, the shadow is the whole thing. The shadow is just as big as the thing, right? So if it is orthogonal, then there will not be any shadow. But if it is along the ground, then the shadow will be, so your shadow will depend on the intuitive understanding of shadow is it depends on angle, right? So if I'm shining light from above, typically your shadow will be shorter than you. And if it is right above the head, there will be no shadow. But if you're lying on the ground, the shadow will be just as much as you, as in you cannot embed yourself in the ground. So that's where your intuition fails, but that is the limiting
Yes,
case.
sir.
That is the, is
Just
that
that
fine?
we cannot see the shadow, but the vector itself is shadowy.
Yes, that's the vector itself is the shadow. So if you think of it as the limiting case of going closer and closer to the ground, your shadow will keep increasing, right? It keeps increasing in length. And at the limiting case, which means you are at the ground, it becomes, you become one with the shadow.
Yeah, one.
Yeah. So, okay, let's not go more into that. But Gram-Schmidt. Next, so all of these things. So if I want to calculate the projection operator, I would want to calculate this projection onto W. But for projection onto W, if you remember, it requires an orthonormal basis. And we have said that if there is an orthonormal basis, this happens, and so on. But how do we come up with an orthonormal basis? That is given by Gram-Schmidt orthonormalization. This I will explain only with an example because explaining it theoretically will be difficult. So let us take, for example, one moment. Let's take xyz such that x plus 2x plus y minus 3z is equal to 0. This is a subspace, right? This is a plane passing through the origin. So this is a subspace. And I want to calculate what projection, I want to analyze what PW is, or projection onto the subspace W is. Let us say I want to calculate PW of 1, 0, 1. So how do I go about doing? What is projection of the vector 1, 0, 1 onto W? First of all, is 1, 1, 0, 1 in the subspace? Is this true?
1, 0. It is not true.
That's not
true.
true. So this
Not
this
true.
does not belong. So you will have some non-trivial projection. So non-trivial projection meaning it will not be the whole thing. So if it were to be in the space itself, then the projection would just be itself. So yeah, 1, 0, 1 is not there. Now I want to calculate what projection of 1, 0, 1 onto W is. But for that, I want an orthonormal basis of W. If I have an orthonormal basis of W, suppose, and this is a two-dimensional subspace, right? Suppose W1, W2 is an orthonormal basis of W, then PW of 101 is equal to projection of 101 onto W1 plus projection of 101 onto W2, right? But what is an orthonormal basis? So first of all, what is the basis of W1, W2?
The point we
Just by
satisfy.
looking at it, can we say some basis?
Yeah.
I can take
1, 1 minus and 1.
1, 1, 1 is okay. And another basis element?
There are multiple. 1, 3, 0.
This is fine?
Yes.
This is a basis, but this is not orthonormal basis. Why? First of all, this is not a unit length vector. This is not a unit length vector, and their inner product is not 0. So it is neither orthogonal nor are any of the vectors of unit length. So to do this, to convert this basis to an orthonormal basis, what we use is known as Gram-Schmidt process. So what do we do is, suppose V1 is equal to.
Sir, I have a question. Can I ask?
Yes.
So in the basis, we can't take 2, 2, 2 because if we take 2, 2, the multiple of first vector.
Yeah, but then that will not be a basis.
Dependent. That will be dependent, sir. In that case.
Yeah, you cannot take that. That's why I took this.
Okay, sir.
These are independent, right? Because one has 0. One is neither of them are multiple of the other.
If they are missing, obviously.
If we keep changing the basis, like we will get different projections, right?
The projection will stay the same. So the projection is independent of the choice of the basis.
Okay.
Yeah.
Like, is it unique for the transformation?
The projection is unique, but you can start out with any basis, and you do Gram-Schmidt orthonormalization to get probably a different orthonormal basis, but they all balance out when you do this. So that is a slightly higher level result, which we are not even going to see the proof of. I don't think even the prof has solved it.
Yeah,
It
I
is just
understand that.
yeah. But
Because I
this
was
is a
working.
well-defined map in a sense that irrespective of what basis you choose for the projection, the vector that you get at the end is the same. You can play around with different bases for specific examples and check it for yourself. But if you want a formal proof, you'll have to take up a textbook.
Okay, thank you.
Okay, so what we do is in Gram-Schmidt orthonormalization, the first step you do is take one of the vectors and normalize them. Normalize them meaning divide by the length to make it a unit vector. So W1, I can just say 1 by root 3, 1 by 1, 1, 1, because this one will become a unit length vector. So I've solved one of three problems. I want both vectors to be normal as well as them to be orthogonal to each other. So the second step is you look at this V2 and remove the component of that from W1. So you have W1 and this is V2. You have some component over here and you have some orthogonal component. So the idea is that V2 can be written as sum of something along this and something perpendicular to this. So look at this guy W2 tilde, which is V2 minus projection of V2 onto W1. So this part is the part that lies along W1. So if I remove that, what will remain is something orthogonal to W1. So I want something orthogonal to W1, right? So V2 as it is 0, 3, 1 minus projection of V2 onto W1 will be just okay, this, yeah, projection of V2 onto W1 is fine. This is inner product of V2 with W1, which is 1 by root 3, 1 by root 3, 1 by root 3, divided by norm of W1 square, which is 1, times W1, so which is 1 by root 3, 1 by root 3. So I get 0, 3, 1. I get a 1 by root 3 common over here, 1 by root 3 common over here. I'll take them all together and I'll put this outside over here. And 0, 3, 1, 1, 1, 1 will give me 4 times 1, 1, 1. Or 4 by 3 times 1, 1. Now if you look at this, this will be 0 minus 4 by 3 is minus 4 by 3. 3 minus 4 by 3 is 9 minus 4. And 1 minus 4 by 3 is minus 1 by 3. So did you get the steps that were done over here? What you have to do is remove projection of V2 from W1. And if you look at W1 and W2 tilde, these will be orthogonal to each other. That you can check. I mean, theoretically, it is established that it will be orthogonal to each other, but there is one more problem that we have not solved. W2 is not orthogonal to W2 is not orthonormal. So this is not a unit vector. So to see the unit vector, you'll have to do 16 plus 25 plus 1, which is 35, 41, 42. So you'll have to do something like W2 is equal to by 9, 3. 3 is 14 by, it's something like this, I think. So what did I do over here? This is actually W2 tilde divided by norm of W2 tilde, so that I get a unit length vector. This is the third step. So first step is divide by, so this was W1 divided by norm of W1. which gives me a unit vector. And then I remove the projection to get an orthogonal vector. So this is step 1, this is step 2, and this is step 3. Now, if you have more vectors, as in if you have a 3-dimensional subspace and you want to find 3 vectors, what you have to do is the V3, you have to do minus projection of V3 with W1 minus projection of V3 with W2. But more often than not, more than 2 vectors, the calculations become cumbersome, and in the exam, you will either have easier numbers to deal with. But the idea is the same, that at every step, you normalize one vector, look at the next vector, remove the projection of the current vector with all the vectors before that. And what you'll end up with is a basis which is 1 by root 3, 1, 1, 1. And you have 1 by root 42 minus 4, 5, minus 1. This is an orthonormal basis. At minus 4, 5, minus 1. If you check if that is in the plane, minus 4, 5, minus 1, minus 8 plus 8 is 0. So that point, that vector lies in the subspace, and it is orthogonal to this. These are normal vectors after normalization. So we have achieved what we want. The final step to compute the projection of the vector is to just do this. Yes, is to just do this.
Sir, please repeat this basis part. I have a confusion here.
Okay, so you have a basis V1, V2, and you want an orthonormal basis because I want to calculate projection, correct? And projection has to be calculated when you're doing projection onto a subspace. It is calculated using an orthonormal basis W1, W2. But just by looking at this thing, you cannot come up with an orthonormal basis, right? So we start out with any basis, which I just saw that these two are linearly independent vectors in the space, which form a basis. And I want to get an orthonormal basis out of this. So the first step to do that is normalize the first vector. So take the first vector and normalize it. Normalize it meaning divide by its norm, W1 by norm W. That will give you a unit vector. That is your first unit vector. Next, you have a vector V2 in the space, but the problem with V2 is that it is not orthogonal to V1 or W1. So I want it to be orthogonal to W1, so I remove the component which is along W1. By that I mean projection of V2 onto W1, I will subtract from V2. And that is a routine computation. It is most of the time, because of the normalization, you'll get square roots, and the thing is maybe technically, as in there is chance for you to go wrong numerically, but conceptually it is clear, right? What is projection of V2 onto W1 is known. It's just using that formula. And you will get a vector which is orthogonal to W1. This procedure of removing the projection from a given vector gives you an orthogonal vector. And this orthogonal vector, however, if I just take W1 and W2 prime, this will be an orthogonal set. But remember that our objective was orthonormal set. So at this stage also, you have to normalize it by dividing by its norm. So to say it in one line, the Gram-Schmidt orthonormalization process is just write out a basis, any basis, not necessarily orthogonal, orthonormal. Take a vector, normalize it. Look at the next vector, remove its components from the previous set of vectors. Then whatever vector you get will be orthogonal to all of those previous to that, and then normalize it. Look at next vector, remove components, normalize it. So it's so on. And if you want a more detailed explanation of this thing, you take a look at the lecture notes. There I've explained it in more steps. I've written down some sort of an algorithm, but at least in this example, you know what's going on, right? So I have computed what is projection of 101.
Excuse me, sir.
Yes.
So the basis only the dimension of the basis would be 2, right? The questions which
Yes.
would be asked in the exam.
There may be 3, but it will not. Typically, the understanding is that it should not be computationally heavy. At least it should be doable in the time that is provided to you.
Okay.
It will be done keeping that in mind.
Okay.
Yeah. So, okay. Now I know what is projection of V on a given vector. This 101 was some particular point. As soon as I get W1 and W2, I can calculate it for any points X0, Y0, Z0 on the space. Now, for this set PW, what is the nullity of PW? What is the rank of PW? What is the nullity of PW? So I'm looking at PW as a map from R3 to R3. Or let us say, what is, first of all, PW of, for example, -1, 2, 0. Can you say what this is? Can anyone quickly?
It would be same.
Yeah, it will be same. Why?
Because projection of same vector.
Yeah, projection of a vector in the space itself is equal to the vector itself. So there will be no loss. So such things are some of the first practical checks that you have to see when a projection of a vector onto a subspace is asked. First you check whether, so here we first check that, right? And we found that in this case, it does not actually belong to W. So we'll have to do Gram-Schmidt orthonormalization to get a basis and calculate the projection. But if this was given, you should not end up wasting time on calculating a basis and an orthonormal basis and then do projection. And well, even if you do that, you will get this as -120 only. These properties come in handy to get rid of certain checks.
Calculations.
Yeah, certain calculations. But if none of these properties give you the answer directly, then you'll have to go to the long method. So that is one thing that you can keep in mind for the exam considerations. But anyway, now back to the question: what is nullity of PW? What is rank of PW?
Rank is 2.
What is rank of PW?
That is 2.
Okay. And nullity?
Is 1.
Yeah. So how did that come? Because rank of PW is the dimension of the image. And the image is actually W, right? The shadows of W, shadows onto W lie in W. And every vector in W is taken care of because if you want something to be a shadow, which is an element of W, you just take
Projection
the
means
projection
that
of
is
that
1 to
element.
function.
Sorry?
Sir, is that projection means the 1 to function? 1 to.
It is not, right? Nullity is 1.
Yeah,
In
yeah,
this
yeah,
case, it is
yeah, yeah.
not.
It is not 1, 1, so it is
So,
not 1 to 1.
so if you look at this plane somewhere in R3, there is this whole line of vectors which give you zero shadow or zero projection.
Yeah.
So, and whatever vector you take, the image lies over here. The image cannot lie somewhere not along the plane. So it's not on. The image is exactly the plane.
Okay, so the image is exactly.
Can you help me understand this W perk for this question?
W perk for this question?
Yes.
Yeah, okay. So it is the orthogonal direction to the plane, right? So if you look at this plane, it is 2x plus y minus 3z is equal to 0. This is the defining equation of the plane. So I can write this as 2, 1, minus 3 dot xyz is equal to 0. Right. So my plane consists of points which are orthogonal to 2, 1, minus 3. Correct?
Correct.
So 2, 1, minus 3 is orthogonal to the plane, meaning its projection is 0. And my perpendicular direction has dimension 1. So the span of 2, 1, minus 3 is actually W per.
Okay. So nullity is 1.
Well, nullity is 1, so you can conclude that 2, 1, minus 3 is the only thing. So in general, if you want to calculate W per, you might not always have this luxury. But given any two vectors, the other vector can be found using, so suppose I'm given 1, 0, 0 and say 1, 1, 0. Well, that would be too simple, but okay, maybe 1, 1, 0, 0, 1, 1. Suppose I have a plane spanned by these two vectors. I want to find the perp of this. So I don't have the equation of the plane. I can construct the equation of the plane and then figure it out. But if I want to say that xyz is normal to both of these guys, I'll say xyz dot 110 is equal to 0, which gives me x plus y is equal to 0. And the second equation will give me y plus z is equal to 0, correct?
Correct.
So I'll have x minus x and x, I think.
Correct.
Yeah, so 1 minus 1, 1 will be a generator for the orthogonal complement, and so on. So the orthogonal complement of a given subspace will always have dimension equal to total dimension minus dimension of the subspace. So that is, we had written that somewhere, right? So this. And then if you take a basis representation of W and then formulate the equations, you can find out basis elements for W per.
Now you're explaining it's like clear, but when we sit to solve the questions, it becomes some complicated. Hard to
Yeah,
visualize
well,
things. Yeah.
yeah, it's practice. Yeah, you just have to keep practicing and it will get natural at some point.
Thank you.
So the last concept is orthogonal. Yes, is there any other doubt?
Sir, one doubt. How you find that the nullity of PW is 2 and the rank is 1? I didn't get that point.
No. Rank is 2 and nullity is 1.
Yes, sir. How do you find that?
So, okay. What is rank? Rank is the dimension of the image, right?
Yes, sir.
And the image of the projection map is equal to the subspace.
Yes, sir.
So dimension of image is equal to dimension of W.
Yes, sir.
Which means rank is dimension of W.
Okay, sir. Okay. Sorry, sir. I got it.
Yeah, that's all right. So rank of PW is actually dimension of image W. Let me just write it somewhere over here. Rank of PW is dimension of image of PW. But image of PW is just W. So that's dimension of W, which is 2. This is a plane, so its dimension is 2. So if rank is 2, then nullity is 1. All right. And the last thing is orthogonal transformations. It's already past 10. So in tomorrow's session, it might be a little bit broken up for you guys because there are some concepts from 6 and some concepts. It's just one concept. So I'll probably ask the TA to take that orthogonal transformation. So there's just a definition of an orthogonal transformation and certain properties of orthogonal transformations.
Sir,
And
is it
ortho,
important?
everything is important. So yeah.
Sir, can you explain something about the rotation? I am very confused with that topic.
I think now I'll take problems, like if there are specific problems, as in numerical problems, and I'll ask the TA to take that. And if you still have doubts, you can look at the instructor session for that, which happened during week 7 or 8. I think 8 it was. There, I think I have given a more detailed explanation of rotations as well. So is that fine? Does that work for you?
I already watched that, sir. Then too, I have some
Okay.
doubts, so that only I'm asking.
Okay. Okay. Let's first I'll ask if there are any other doubts, as in if there are any numerical problems that I would you would like me to solve, and then later I'll take up that.
Yes, sir. Yes,
Okay.
sir. I have.
Yes, sir. Yes, sir.
Okay.
Sir, it's from practice assignment
Okay.
of week 7.
Week 7, which one?
Yeah, question number 6, sir. Sir, I have just
Practice assignment.
yeah, week
Week
6.
7. 7 you said, right?
Yeah, sir. Week 7,
Question
practice
6.
assignment, question number 6.
Okay. Let me L prime be affine spaces. Let L is U. L prime is spaces. Does everyone have access to this, or should I write it down? It's better for me to write it down, I think.
Sir, I have solved the question, but
Okay.
I got the wrong answer. Sir, I am just trying to say the approach. Just
Okay. Basis for U given by this. Just
if
give
you
me a
allow.
moment.
Okay, sir. Okay.
Let me see. Okay.
So
Yeah,
if you
yeah. What
allow
is
me,
your doubt?
can I see the approach?
What do you want to do?
Yeah. So first of all, if we're looking for the first option, that in the question they are telling us that L is equals to U, and U is a subspace, and they are given the basis, and basis is nothing but the span of the subspace.
No, the subspace is the span of the given basis.
Yeah. Sorry, sir.
Yeah.
So in that case,
That's
we
fine.
can represent a linear transformation of the basis.
No, the first two options. So okay, U is equal to span
Yeah,
of
U is equals to is the span of the basis.
201,
Yeah, 110 and
110,
010.
010. Right?
Yeah.
Now, the first question is what is L? The second question is what is L prime, but let me get there
L
later.
is a
This is
affine subspace.
so wait. 101 and 01.
Yes, sir.
Okay. So how many basis vectors do you have over here?
3, sir.
And you're in R3, right? These are
Yes.
affine subspaces of
Yeah.
R3.
It represents the
So,
number of
and
couples.
these are, can you see that these are linearly independent?
Yes, sir.
So this has to be what?
Sir, it is a spanning set. No.
No. What is the span of that?
Basis.
Sir,
So I'm claiming that this is R3.
yes, sir.
Why? Because any linearly independent set of size 3 is a basis for R3 itself, right?
Yes, sir.
So span of 3 linearly independent vectors in R3 has to be R3,
Yes, sir.
right? So
Yeah.
L is equal to R3 is fine.
Yes, sir, that is fine.
Okay. Next, what do we have? You have U prime to be span of 101 and 011.
Yeah, in that case, it is not will be L is not equal
It
to
will
R.
not be. U first we'll see what U prime is. How do I write this? X plus Z is 0. There's a 1 minus 1, 1. So x, y minus z. So this is x plus y minus z is equal to 0. This is the plane which is defined by x plus y minus z is equal to 0. Right?
Okay, sir.
Is that okay?
Yes, sir.
Yes, sir.
But then I am shifting that by 201.
Yes, sir.
Then I will get something of the form x plus y
Yes.
minus z is equal to d.
Yes, sir.
So L prime will be x plus y minus z is equal to d. Correct? Now what is the d? I know that 201 is in my L prime.
Yes, sir.
Correct? So this implies 2 plus 0 minus 1 only. Sorry, this is 1 is equal to d.
Yeah. 2 0 and
Which
1.
implies d is equal to 1.
Okay.
Right? Sorry. Yeah. Then L prime is actually x plus y minus z is equal to 1. Is this clear?
Yes, sir. It is clear.
This was the part you had a doubt about?
No, sir. I have doubt in the options, like
Okay.
the linear, the affine subspace, like L equals
Okay.
to U.
L is equal to U.
Yes. And
Which
the
option do you have a doubt in?
so all the options and the two options are
So
already
the
discussed.
first four are fine, right?
Yes, sir. Yes, sir.
After this discussion, the first four are fine. So the first four concern what is L and what is L prime.
Yes, sir.
So that is done.
Yes, sir.
Now I have that f of xyz is equal to, or f of, he says u, but I'll just call it xyz. F is a map from L to L prime, but L is the same as u, which is the same as R3. So I'm writing xyz only. For any xyz, I have 201 plus t of xyz.
Yeah.
Right?
Yes, sir.
If you want to, you will have to figure out what t is, first of all. So let us see what is t. It says that t of 010 is 0. T of 201
is 0, 1, 1.
011.
And T of 1,
T of
1, 0 is equals to 101.
this is 10, right?
Yeah.
Using these three pieces of data,
Yeah.
you should be able to write what t of xyz is, right? Because this object is a basis.
Yes, sir. We can write it a into 0, 0 plus b into 0, 1 plus 1 and c multiply with
Yeah,
1.
so you already have what t of e2 is. T of e2 is 000.
Yes, sir.
You want what is t of 1, 0, 0. But what is T of 1, 0, 0? T of 1, 0, 0 is T of 1, 1, 0 minus T of 0, 1, 0. Right?
Okay. So why should I do this?
So I want an expression. Okay, let's break it down further. I want an expression for what T of xyz is, correct?
Yes, sir.
I'll know that this is T of x times T of 1, 0, 0 plus y times T of 0, 1, 0
Yeah.
plus z times T of
101.
1, 0.
Yeah.
This part I know is 0.
Yeah. 0,
Okay,
1,
so
0
I
by
want to figure out this. Sorry, one. What have I written here? 0, 0, 1. Right?
Yes, sir.
So I know T of 0, 1, 0 is equal to 0 by the given data in the question. Now I want to figure out what T 1, 0, 0 is and what T 0, 0, 1 is.
Okay.
So what has been given to me is the value of T on some 3 linearly independent vectors. Using that, I can find the value of T on any vector. This is how you can use a basis to determine a linear transformation. In our particular case, 1, 0, 0 can be written as 1, 1, 0 minus
Minus 0, 1, 0.
0, 1, 0. So due to linearity property of T, I can have T of this is T of this minus T of this.
Yes, sir.
But then T of this is 0 again. So this is just 1, 0, 1.
Hmm.
Okay, so this is T of, just a moment. This is one important information. This is T of E1. This is another. And the third one, I want to know what T of 0, 0, 1 is. So how will I write T of 0, 0, 1? There I'll have to do some linear combination tricks. Can you quickly see?
For that, I think we have to take T201 and T110.
So you have 220 plus 0 minus 2, 0. Well, I'll just do minus 2, minus 2,
Minus.
minus 2, minus 2, 0, and 0, 2, 0, and 2, 0, 1. This should work, right?
0 minus 2, 0.
Yeah.
Correct. Sorry.
This should be fine. So
Yeah,
this
it's
is
fine.
T. Yeah. So the concept that is involved is finding out the expression for T of x, y, z using the images of the vectors that is given over here. But this is nothing but minus 2 times 1, 1, 0 gives me 1, 0, 1. So I'll just write it as this. Plus this is 0 anyway, second part. 2, 0, 1 I know to be 0, 1, 1. So this is minus 2, 1, minus 1. This is T of E3. Right? So I have T of E1, T of E2, T of E3. And I know what T of XYZ is, right? T of XYZ is X times T of E1. So T of E2 is 0. So I'll forget about that. I just need 1, 0, 0 and 0, 0, 1's images. So it's X times 1, 0, 1 plus Z times minus 2, 1, 1 minus 1. This is X minus 2Z
Z.
Z and X minus
X
Z.
minus
Hopefully
Z.
I've not made any mistakes. Now this is T. And what we want is expression for F. For that I need to add a 201. 201 was the translation vector, right? Yeah, 201. Wait, no. Yeah, 201. 201 gives me this. And that is option number 5. So the main thing that was involved over here is not actually understanding affine transformations, but figuring out what the definition of T is when the value of T at given 3 linearly independent vectors are. So you have to write the standard basis in terms of the given basis. So this 1 0 this is also a basis. So you have the you have the definition of the linear transformation on these 3 given vectors. And for the standard definition, you want it on the vectors 1 0 0 0 1 0 and 0 0 1. Fortunately, one of them is directly given and the 2 others are not far off. And you have to figure out the definition of T of XYZ and just add this 201 to it, which gives you the answer.
Sir, I have a question.
Wait, were you the person who asked this question?
Yes, sir. Yes, sir.
Okay, then fine. Yeah, go ahead.
Sir, in the question, they mentioned that f of u equals to 201 plus t of u. So in that case, yes, sir. In that case, t of u can be represent as like I want to represent t of u like t of x comma y comma z equals to a of t of 201 plus b into t of 110 plus c into 10
Okay, let me
10.
write down what you're saying. So f of xyz is given to be 201 plus t of xyz.
T of u. I want to calculate the t of xyz separately, then add it to that.
Okay.
So
that's what we have done over here.
But why we are using the standard basis, sir? I don't understand
You
that
don't
part.
need to use the standard basis. You can write this as, so for x and z,
Can you write as
let
this?
me.
My.
I'm so sorry to interrupt, but if we use different bases, we will get different transformation.
No, I'm just trying to write in the given basis. They are providing in the question.
Sir, I'm
So you can write this. Just a moment. Just a moment. Minus 2. X of. Okay. So here I'll have x comma y comma z is x times 100, which is. So, okay, I'll call this guy V1 as 010. V2 is 201. And V3 is 110.
Yeah, I'm just, yeah.
Okay, so you want me to write it in terms of this basis, right? V1,
Yes,
V2,
sir.
V3. So I can write this as, this is V3 minus V1 plus Y times V1 plus Z times 220 minus 2 V3 plus 2 V1 plus V2. Do you see? I've just done the same thing, but I've just written it out like this now. So V3 minus V1, if you look at V3 minus V1, it is nothing but 100. V1 is just 010, and E3 is minus 2 V3. Whatever I've done over here, I've just written it over here. So you can verify that this is true. So for V1, I'll have minus x plus y plus 2z V1 plus 2z, no, not 2z, just z V2 plus x minus 2z v3. So this is the expression for that using your standard basis. You can check this. Is this clear to you or are you confused?
I'm totally confused now.
Okay, wait. You want to write t x y z, right? T of
So can you
x
write
y z.
adjustment what I am saying?
Just one moment.
Okay, sir.
So I x minus y plus 2z. Ah,
So one of the tutorial video they are using another method, I think.
no, the methods may be different, but the
Yeah.
answer should be the same. 201 plus add. Yeah, I might not be using the most optimal fastest method. Is this 110 was it was, yeah, 110. So this you can verify to be true. This is xyz or this is t of this.
Okay.
And this is what you meant, right? So I want you, you wanted to write any given point in terms of this basis, 010, 201, and 110. And this is how you would do it. Anyway, now what were you proposing? What were you saying?
Can I say?
Yes, please.
Regarding this transformation, sir, with respect to different bases for domain and codomain, we get different matrices.
You
So,
get
sir,
different matrices, yes. Yeah.
So, sir, when we trace back the matrices, we multiply x, y, z, like whatever do. I'm getting different linear transformation.
You should not get the different linear transformation. Why is that? As in, why are you getting, like, are you working with a specific example which you would like to
P by
discuss?
Qs. I'm working on P by Q, and they're like tracing back the from matrices. I'm going back towards the transformation. I'm getting some different transformation.
Okay, which problem? So wait, just a minute. So is this doubt clear? Is this fine or no?
I understand what you were trying to explain.
No. I'm asking the person who raised this doubt.
Just I need to watch that part one more time, and then.
Okay, you take a look at this.
Yes.
Yeah. So writing any vector xyz in terms of a given basis is typically done like this by solving for some system of equations. And this is the solution to the system of equations. Minus x plus y plus 2z, z x minus 2z. This is a system, and then using whatever values you know. So this part will be 0 because t of 0, 1, 0 is 0, and then the images of these are known, and then you can figure out what t of x, y, z is. Okay. So second question is what? Shivam?
Yes, sir. My PYQ question is there, sir.
Where is PYQ? In which weak section or
May 23.
Can you? Is it there on the portal? Is it there on the?
No. It's not there on the portal.
He's
Oh,
talking
it's
about
not there on the
previous term
portal.
question.
Or can you write the this transformation? I will just dictate it.
Yeah, that's fine. Yeah. Huh.
So transformation given over here is from R3 to R3 T X Y Z.
Yeah.
The first component is x plus y plus z.
Okay.
The second component is x minus y minus z, and the third one is x. Standalone x.
Okay. Okay.
and then it is given that there is a matrix A, and the elements of the matrix are A, B, C, D, E, F, G, H, I.
This way, right?
Correct.
Okay.
With respect to bases 1, 1, 1.
1, 1, 1.
1, 1, 0. And 1, 0, 0.
1, 0, 0. Okay.
Yeah, for both domain and codomain. So we have to
Okay.
find 2b plus 2e plus 2h.
Find
2b.
2b, right?
Plus, yes, plus 2e plus 2h.
2h. Okay.
The matrix I am getting for this one is 1, 1, 1.
Wait a minute.
Okay, sir.
So to write what A is, okay, wait, candidate solution. What is your solution?
The matrix I am getting for this, with respect to this spaces, is 1, 1, 1.
1, 1,
in row
1.
wise. -2, -1, 0. 4, 2, 0.
4, 2, 0.
This is the matrix.
Okay, let's verify if this is correct.
Okay.
So yeah, what do you have to do to find the matrix? First, you have to calculate what?
Apply the transformation on it.
Apply the transformation on each of the basis vectors. The first
Yes,
basis
sir.
vector is 1, 1, 1, and the image of that is 3
Minus
1
minus
one.
1. Right. And this is 1, 1, 0. This would be 2, 0, 1. And this is 1, 0, 0.
1, 1, 1.
This is 1, 1. So T of, I'll call them V1, V2, V3. So one thing is obvious. T of V3 is V1. T of V1 now, I need on 3 minus 1, 1. So do you, is this correct? Let us see. 1, is it V1 minus 2V2 plus 4V3? This is what we want. This is your candidate, right? So 1, 1, 1. So you have 1, 1, 1 minus 2, 2, 0 plus 4, 0, 0. So that's 1 minus 2 minus 1 plus a 3 is correct. 1 minus 2 minus 1, that's correct. 1 minus 0, this is correct. Yeah, this seems to be correct. You seem to have done the correct thing. And what is this? V1 minus V2 plus 2V3. That also 1, 1, 1 minus 1, 1, 0 plus 2, 0, 0 gives me 2, 0, 1. Yeah, this is correct. This is correct. So yeah, what is the doubt now?
Sir, in this matrix, if I'm multiplying this x, y, and z, I'm not getting the transformation back.
You will not get the transformation back because so what is the matrix representation? So if I have A to be the matrix representation with respect to, say in this case, just beta gamma. So M of T beta gamma. What does this mean? This means that if I do the multiplication of M of T with respect to a vector or a column vector with coefficients, for example, let's take examples to show the thing. You want to know what T of xy, you want to recover what T of xyz is
Yes.
given this matrix, right?
Yes, sir. Yes, sir.
So question is, given A is equal to this matrix with respect to the given basis beta, what is
T of x.
yeah, T of xyz. But what is this beta? This beta is 1, 1, 1. What was it? 1, 1, 0 and 1, 0, 0. So when you say T of xyz, you should not do A times xyz. That only works for the standard basis. What you have to do is A times. So let us take, for example, T of 1, 0, 0. Once again, if I get T of 1, 0, 0, T of 0, 1, 0, and T of 0, 0, 1, I'll be done, right?
Yes.
So T of 1, 0, 0 is actually, this is just T of V3, right? In this case. And T of V3 is
1, 1, 1.
A times 0, 0, 1. And A times 0, 0, 1 is 1, 0, 0. Am I doing good? 1, 1, 1 is what I want. Wait. Okay. If I look at A 0, 0, 1, I'll get the last column of it, which is 1, 0, 0, which is V1, which is 1, 1. I'll tell you what has happened over here, and I think the rest of the things that you can figure out. So
yes,
but you don't understand this part, right?
No, I didn't understand.
Yeah. So I want to figure out what T of 1, 0, 0 is, but I am looking at in terms of this basis. I'm writing it as T of V3. Now the vector V3 in the coordinates of the given basis is 0, 0, 1, correct? It is 0 V1 plus 0 V2 plus 1 V3. So this vector V3 in the new system is actually 0, 0, 1. So when you're going from transformation to matrix multiplication with respect to the given basis, it happens the matrix multiplication of not the vector in standard coordinates. You have to have the vector in the new coordinates. Do you get this? Did you get this step?
Like I will have to work on this.
No. If, so okay, you want to calculate what T of V3 is, right?
Yes.
So you will not do A times 1, 0, 0, because 1, 0, 0 are the coordinates of the vector V3 in the old system. This will not give you your answer. So what are coordinates? Coordinates is every vector can be written as a linear combination of the given basis, right?
Yes.
And these coefficients that you have over here, these are called the coordinates. So
Acha.
coordinates of V3 are 0, 0, 1 in the new system. So what you need to do is multiply the given matrix, whatever it is, with the coordinates of the vector.
Okay.
Okay, and in this case, you will get 1, 0, 0. Okay, because here, like you'll get the third column. When you multiply with 0, 0, 1, you'll get the third column. But then again, even this is not the vector, but this is the coordinates of the vector in the new system. So this is actually V1 plus 0, V2 plus 0, V3. But V1 in the old system, now this is the place where you might find it a little bit difficult because we are switching between systems and not really making it clear what system we are writing it in. And this is also something that comes with familiarity and experience and whatnot. So this is actually V1. So if let us do one more thing, and maybe it will be clear to you. If I want to look at T of 0, 1, 0, what is 0, 1, 0? In this system, what is 0, 1, 0? I have to remove some things. It is V2 minus V3, yes?
Yes.
Right.
Zero.
V2 minus V3 is 0, 1, 0. If I want to find the image of 0, 1, 0, 0, 1, 0, I'm writing in the standard coordinates. This is actually my matrix A times V2 minus V3. So that is 0, 1, minus 1. Okay, so this is like 0 V1 plus V2 minus V3. So these are the coordinates of the new guy. So if you're using the matrix with respect to a basis, you have to multiply the coefficients of the given vector with respect to that basis. So let's see this. 1, 1, 1, minus 2, minus 1, 0. 1, 1, 1. Can you tell me the last? It's what? 4, 2, 0. Okay. 4, 2, 0. If I do this, what will I get? 0, minus 1, and 2. Now these are coordinates again. This as a vector is minus V2 plus 2V3. So what is this? Minus V2 plus 2V3. Minus V2 plus 2V3. This is 1 minus 1, 0. Correct? So this is 1, what was it? 1 minus 1, 0. Yeah. And if you check that, that is correct, right? 1 minus 1, 0 is correct. So this is equal to this. So when you are using matrix multiplication to determine the value of some vector, if you use a matrix with respect to beta, these coordinates also should be with respect to beta. And the answer that you get will be the coordinates of the vector with respect to gamma, whichever basis you choose on the codomain. But in this case, you're choosing the same basis. So then to unravel that, you have to again write it as V1 minus whatever. If you get ABC as the answer, it is AV1 plus BV2 plus CV3.
I can understand what you're trying to say.
Okay, okay. Yeah, you can take a look at some other videos as well. And this is something that, yeah, you get as you calculate more and more. So
yes, playing with matrices and all.
Yeah, yeah.
Thank you,
And
sir.
yeah, the immediate thing you can do is do T001 and conclude that it should be equal to what? Z only, 1 minus 1, 0. You try to get this. If you get this, I think you will have understood what is going on. So to do this, what you have to do is express 001 in terms of the given basis. Look at the coefficients, form its coefficient vector, multiply the coefficient vector with the given matrix, and you will get the coefficient vector of the image, and then unravel the coefficient vector using the values of V1, V2, V3 that you know, and you should end up with this.
Okay, sir, I will try. Thank you.
Yeah, yeah. And last question, please. Then I'll have to wrap up. Yes, Harita.
Sir, no, sir. I was having a similar question, sir. If I understood properly, if we write the matrix in terms of some other basis other than the standard basis, and if we
Yes.
and if we